All right, time to hop to some part two of two variable statistics. This is the same slide we had in the previous video. Look at all this stuff we got done in part one. Hey, go us. That was you and me high-fiving. This is what we're going to work on in this video. We're going to talk about residuals, the appropriateness of a linear model, and influential points, outliers, and transformations of data. So let's do it. All right, a residual is the difference between the predicted value of y and the observed value of y. So y minus y hat. Residuals exist because our model can't answer every question we ask it, right? It's not going to be perfect. We're just hoping it's really good. The residual then is the error of our estimate. If we plot the residuals, so we take the residuals on the vertical axis and the x value on the horizontal axis, that's called a residual plot. That's going to show us a visual representation of all of the error. We don't want to see a pattern in this. Because if we see a pattern in this, that means there's a pattern to our error. If there's a pattern to our error, this was probably a pretty bad model, because that means we're consistently doing something wrong. So that's always a really great way to actually check for the appropriateness of a linear model. See if there's a pattern in the residual plot. Influential points and outliers. Believe it or not, influential points and outliers are not the same thing. So an outlier could be an influential point, but it doesn't have to be. Right? I could just have a value of x that's just way bigger than the rest of them, but it's still following the pattern of the data. So, yeah, that. An influential point is one that, if removed, would have a significant impact on the slope and/or y-intercept, usually both, of the regression line. An outlier has an unusually large residual when compared to the residuals of the rest of the data, but taking them out might not affect the regression line. Transformations of data. So sometimes we were talking about 2 slides ago, like not even 45 seconds. Sometimes a linear model is just not appropriate. Like if my data, that's an eraser, not a pen. My data looks like that. Clearly that does not align. Okay, maybe it's not that clear, but that's supposed to be an exponential model. So there are all these transformations that we can do to straighten out the data. If we see that the curve, or if we see the scatter plot looks like an exponential function, so it looks like that, then what we do is we transform all the y's by taking the log of them, and that will straighten it out. If the data look like this, logarithmic, then you take the log of the x's, and that straightens it out. Now a power function looks stupidly similar to an exponential, but it's something like a quadratic function, right? So that's me drawing a parabola really poorly. You take the log of both x and the log of y. So there's a table to help you remember them. That said, the AP exam usually tells you what transformations it wants. And that said, transformations usually just doesn't show up on the AP exam that much. But these are the transformations that you would do. Let's do problems. This is the same problem that we started in part 1 of this video. It's a manager of a grocery store selects a random sample of 11 customers and wants to investigate how many customers in line versus how long it takes to check out. One of the data points was determined to be an outlier. I think it's pretty obvious when you look at the graph which one is the outlier. There's only one that doesn't literally just sit inside the pattern of the data. Circle the point on the scatter plot and explain why this point is considered an outlier. I'm going to circle that point. It's pretty obvious it's that one, right? And we need to talk about why we think it's an outlier, and we need to explain that relative to the other points. So what I mean is, we can't just say it's far from the line. We can't just say it's far from the other points. So we need to kind of talk about both of those together. So this point is an outlier because it has a much larger residual than the other data points. And that would be a sufficient answer. I remember they were actually very picky about this, but this is really all you got to put. You just need to consider the fact that it's much farther away from the regression line than the other points. You have to consider in the context of all of the other points that it's big. is far away. All right. Researchers studying a pack of gray wolves in North America collected data on the length x in meters from nose to tip of the tail and the weight y in kilograms of the wolves. A scatter plot of weight versus length revealed a relationship between the two variables described a positive, linear, and strong. The data collected from the wolves were used to create the least squares equation y hat equals negative 16.46 plus 35.02x. One wolf in the pack with a length of 1.4 meters, so that's an x value, had a residual of negative 9.67. Remember, residuals are y minus y hat. What was the weight of the wolf? So they want to know what was the actual y value. What was the actual weight of the wolf? So I have x, I have, do I have anything else? I have y minus y hat. So I know y minus y hat is equal to negative 9.67. So y should be equal to y hat minus 9.67. Just did a little algebra there to move the y hat over. Well, I don't have y hat. Oh, but yes, I do. All I got to do is plug x into that. So my y hat should be negative 16.46. Well, I didn't write any of what I needed to. Plus 35.02 times 1.4. That's my y hat. Now I'm getting my handy dandy TI Inspire. TI sponsor me. Negative 16.4. No, I don't want to save this document. Silly TI Inspire. Plus 35.02 times 1.4. So my y hat is 32.568. So then I can do this. Y equals 32.568 minus 9.67. And that's y equals 22.898. So let me recap that. I knew the residual, y minus y hat, was negative 9.67. That's what this whole thing is. I knew that if I could figure out what y hat was, it was just an algebra problem. So I figured out y hat by plugging x into this. Okay. A simple random sample of 9 students was selected from a large university. Each of these students reported the number of hours he or she had allocated to studying and the number of hours allocated to work each week. A least squares linear regression was performed and part of the result in computer output is shown below. Man, I read that like a robot. Anyway, the scatter plot below shows the display. The scatter plot below displays the data that were collected from the 9 students. After point P, labeled on the graph of the previous page, not the previous page, this page, was removed from the data, a second linear regression was performed and the computer output is shown below. Does point P exercise a large influence on the regression line? Okay, so the regression line with point P, so this goes with this, right? Point P is in this still. So the regression line is y hat equals 0.4919x plus 8.107. This is the no P regression. Y hat equals 0.1500 plus 11.123. Oh, I forgot the x right here. Okay, so yeah, look, it's got a huge influence, right? When P is removed, both the slope and the y-intercept change. A bunch of other stuff changes too. Look at the r squared. It goes from 47.6% to 2.5%. That's huge. So our answer is yes. With point P removed, the slope decreases from 0.4919 to nearly 0, and the y-intercept increases by about 3. Now you can talk about a lot of more things, right? You can talk about the R-square. You can talk about some other stuff that you haven't seen before this video. But you just need to talk about, like, in general, you need to make sure you hit a couple things. When I looked at the scoring guidelines, it said you needed to hit 2. 2 would have given you full credit. So just make sure you're mentioning a couple things that changed. Don't just say 1, because 1 change isn't necessarily considered significant. Oh, I thought it was done. I was really excited for that to be the last slide. Anyway, we got one more. 2 variables x and y were measured for a random sample of 25 subjects, and 2 separate regression models were fit to the data. Least squares estimation of the parameters in model A yielded the following equation in residual plot. Oh, look, they did some transformation stuff, but without even really doing transformations. It says log y hat equals 0.264 plus 0.230x. Then below it says least squares estimation of the parameters in model B yielded the following equation. Log y hat equals 0.251 plus 0.281x. So one for the top one, model A, they did log and log. And for model B, they only did log. All we're asking, though, this doesn't even really care about the logs. It just wants to know which model is better. Well, if I look at the residual plots, for model A, there's a clear pattern here, right? This, like, there's nothing, it's very scattered, it's all over the place, which means B is better. That means there is less of a pattern to our error. So model B is appropriate, so let's eliminate A and C and E. We're either going to say B or E. Model B is a relationship between x and log y, not x and y, so that means this is wrong. And that's E. And that's the, oh, I just copied this. Foolish me. Say goodbye, Mr. Weber. Bye, Mr. Weber.